The most powerful construction machines ever, infrastructure and megaprojects. Can humans truly reshape the earth at will? And music, what immense forces, machines, and vision drive the creation of massive infrastructure projects worldwide? The arrangement works of the Girder RN09 road in Algeria, carried out by Osgun Insat, represent a highly complex engineering project aimed at modernizing a yet challenging transport route. This 7.66 kilometers section lies between the towns of Borgira and Girder, forming part of the national road that connects the provinces of Baia and Sétif. Originally constructed in 1865 during the French colonial period, the existing road was extremely narrow with a width of only 3.5 to 4 m and no longer met modern transportation standards. The terrain along the route posed significant engineering difficulties. On one side, the road borders steep fractured rock slopes, while on the other, it overlooks a stream located 30 to 50 m below. To overcome these constraints, Osgun Inside implemented a range of advanced structural solutions. The project included the construction of viaducts supported by concrete piers and steel beams, as well as specialized half-bridge structures designed to maximize stability in limited space. One of the most innovative aspects of the project is the use of pre-tensioned beams known as STK'd. These beams enable the creation of a cantilever extension ranging from 2 to 5 m toward the stream side, effectively widening the roadway without extensive excavation into the rocky slopes. This unique design ensures both safety and efficiency while preserving the natural terrain. In addition to these structures, the project involved extensive earthworks, including the construction of open box coververts for water management and tunnel sections to improve route continuity. Overall, the Girder RN09 road project demonstrates a sophisticated integration of modern engineering techniques to transform a historic but inadequate roadway into a safer and more reliable transportation corridor. The heavy-duty crane begins its challenging journey at a steep, winding mountain road, carefully navigating each narrow curve. The massive machine, designed to handle enormous loads, now faces a different kind of test mobility under difficult terrain conditions. As it slowly ascends, the limited width of the road leaves almost no room for error, with sharp bends demanding precise steering and constant adjustments. The crane's operator maintains extreme concentration, coordinating with ground personnel to guide the movement and monitor clearances. The uneven surface and tight switchbacks put immense strain on the vehicle's stability and traction. At certain points, the crane struggles to maintain momentum, its heavy weight working against it as gravity pulls it back. As the incline becomes steeper, the situation intensifies. The crane begins to lose its tire, slipping slightly on the rugged surface. Progress slows to a near fault, and the risk of sliding or tipping becomes a serious concern. The crew quickly reacts, assessing the situation and preparing contingency measures to prevent an accident. Careful repositioning and control throttle adjustments are attempted to regain traction. Every movement is deliberate, as even a minor miscalculation could lead to dangerous consequences on such a narrow, twisting path. The operation highlights the complexity of transporting oversized machinery through difficult environments. Ultimately, this moment serves as a powerful reminder that even the most advanced heavy equipment can face unexpected challenges when operating outside control conditions where terrain and route limitations become critical factors. Come on. Hold-in-place recycling is applied to restore chip-sealed pavement by adding 1.25 in of coarse aggregate including both structure and durability. The process begins with recycling the existing pavement using CSS1 emulsion, which helps bind the reclaimed material and aggregate into a stable base. The operation features specialized equipment, the Work County Loop 3800 recycler for milling and mixing, a Weiler wind elevator for efficient material transport, and a vertical vision paper for smooth and precise placement. By integrating new aggregate into the recycled mix, the pavement gains additional strength and extended service life. CIR with chip seal and additive block is a cost-effective sustainable method that reduces waste while delivering high-quality results. Eat, 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 eat. The process begins with the careful preparation of a 30 m long pipe pile at the job site of the Marine Discovery Centre in Hamilton, Ontario. The pile is first inspected to ensure it meets alignment and structural requirements before lifting. A crane is then positioned to handle the long and heavy steel element using appropriate rigging to maintain balance during the lift. Once secured, the crane slowly hoists the pipe pile from the ground and rotates it into a vertical orientation. This step requires precise coordination between the crane operator and ground personnel to prevent swinging or misalignment. The pile is then guided into the Birmingham vertical travel lead, a specialized frame designed to hold and stabilize piles during driving operations. Workers carefully align the pile within the lead to ensure it is perfectly vertical, as any deviation could affect installation accuracy. Compared to the old United, normally you expect to hear, which is deafening in itself, these newer bra skill that it takes to say he's got quite a touch there. That hammer probably weighs somewhere in the order of like the cylinder alone 4000 hammer. Sure, that weld all that looks pretty good. Well, that's funny with this job. All the welds are tested on top of every single weld, right? Which is in the world certified after the world. But we had an inspector check, which is not normally on this one. After positioning, the Birmingham diesel impact hammer is mounted on top of the pilot. The hammer is connected and checked to ensure proper operation. Once all safety and alignment checks are completed, the driving process begins. The diesel handle repeatedly strikes the top of the pile, generating high impact energy that forces the pile downward into the ground. Throughout the driving operation, the pile's verticality and penetration depth are continuously monitored. Adjustments are made if necessary to maintain alignment within the lead. The hammer continues operating until the pile reaches the required depth or resistance criteria, indicating sufficient load-bearing capacity. The installation process of the Vegamate offshore wind farm began with seabed preparation. Scour protection was installed using the fall pipe vessel rock piper, which precisely placed rock material around each foundation location to prevent erosion and ensure long-term stability. Meanwhile, a total of 67 XXL monopiles were designed and fabricated in Rostock, Germany. After completion, These massive structures were transported on barges through the Kiel Canal to the feeder port in Eemhaven, Netherlands, preparing them for offshore installation. The installation vessel Sela was then mobilized, equipped with a Specialist 650-ton double-level pile gripper frame. This advanced system enabled safe handling of monopiles even under challenging sea conditions. Each monopile measuring up to 85 m in length, 7.8 m in diameter, and weighing as much as 130 tons was carefully appended from a horizontal to a vertical position. Once positioned, the monopiles were driven into the seabed to the required depth. During this operation, noise mitigation systems such as the hydro sound damper and double big bubble curtain were deployed to reduce underwater noise impact. Heat. After installation, a survey tool was used to measure the top flange with laser precision, ensuring accurate alignment. Transition pieces and SUBC anode cages were transported from Aalborg, Denmark to Eindhoven and then offshore. Before installation, marine growth was removed from the monopiles, followed by the installation of SUBC anode cages for corrosion protection. The transition pieces were then lifted and installed onto the monopiles. Finally, the structures were secured through bolting and grouting, completing the foundation installation phase. The assembly of the girder launching beam is carried out systematically on the ground to ensure accuracy, safety, and efficiency before operation. First, the main structural components, including the longitudinal girders and support frames, are delivered to the site and arranged according to the installation plan. These large steel sections are then lifted by cranes and carefully aligned on temporary supports. Next, the main beam segments are connected using high-strength bolts and precise fastening techniques to form the complete launching girder structure. During this stage, technicians continuously check alignment and levelness to guarantee structural stability. After that, auxiliary systems such as the front and rear support legs, winches, and lifting trolleys are installed onto the main frame. Following mechanical assembly, music, hydraulic and electrical systems are integrated, including power units, control cables, and synchronization devices. Each connection is tested to ensure proper functionality. Finally, a comprehensive inspection and trial operation are conducted on the ground, confirming that the beam launcher is fully assembled and ready for safe lifting and launching operations. In 2021, Vorzea demonstrated its expertise in special transport services by handling a wide range of challenging deliveries across harsh Arctic environments. Operating under extreme weather conditions, the company utilized versatile and highly specialized equipment to ensure safe and efficient logistics. The process begins with detailed planning where each transport is carefully analyzed based on load dimensions, weight, route conditions, and weather forecasts. Given the icy roads, low temperatures, and limited daylight typical of Arctic regions, precision and preparation are critical. Specialized trailers, modular transport systems, and heavy-duty trucks are selected to match the specific requirements of each load. During execution, operators navigate through snow-covered roads, frozen terrains, and narrow passages, often requiring escort vehicles, and real-time coordination. Advanced handling techniques are applied to maintain stability and safety, especially when transporting oversized or heavy cargo. Hydraulic systems and adjustable platforms allow for flexibility when dealing with uneven surfaces and difficult terrain. Despite the demanding conditions, Borzola Way maintains strict safety standards throughout every stage of the operation. Continuous monitoring and experienced personnel ensure that each transport is completed without incident. Overall, the company's performance in 2021 highlights its capability to deliver reliable special transport solutions even in some of the most extreme environments on Earth. There we go. Work began precisely at 0:30 on Good Friday morning, immediately after the final train had cleared the line. With the railway officially closed for possession, crews moved quickly to begin the first critical stage, removing the existing track and preparing the site for installation. The rails were carefully lifted using specialized machinery while fastening systems and sleepers were dismantled and set aside. Following this, excavation teams removed the ballast, the crushed stone layer that supports and stabilizes the track using excavators and loaders working in continuous shifts. This process required precision to avoid disturbing the underlying formation more than necessary. Once the ballast was cleared, the subgrade was exposed and leveled, creating a clean and stable working platform. Any unsuitable material was excavated and replaced to ensure proper load-bearing capacity for the new structure. Crews then carried out detailed checks on alignment and depth, ensuring that the excavation matched the exact dimensions required for the underbridge installation. Throughout this phase, strict safety procedures were followed as multiple teams operated heavy equipment in a confined area under intense time pressure. By the end of this stage, the railway corridor had been completely cleared, leaving an open trench ready to receive the pre-constructed bridge sections. With the site fully prepared, the installation phase began immediately. Large cranes and synchronized lifting systems were deployed to move the massive precast concrete bridge sections from their staging area beside the track into the excavated gap. Each section was carefully lowered into position with millimeter-level accuracy, guided by engineers and surveyors to ensure perfect alignment. The placement sequence was critical as each segment had to fit precisely with the next to form a continuous and stable underbridge structure. Once all sections were installed, crews secured the joints and completed structural connections to ensure the integrity of the bridge. Backfilling operations followed with engineered material compacted around the structure to provide stability and support. Immediately afterward, the railway track was reinstated. Fresh ballast was laid and compacted. Sleepers were repositioned and rails were reinstalled and aligned to strict tolerances. Final inspections and testing ensured the track met all operational and safety standards. By 10 o'clock on Eastern Monday, the railway was fully restored, ready for the safe resumption of train services just hours later. The Teju Highway project is a major infrastructure development designed to enhance regional connectivity through a modern 48 kilometers roadway. The highway is planned as a dual carriageway with 3 lanes in each direction, ensuring high traffic capacity and improved transportation efficiency. Along the route, The project includes an impressive network of engineering structures. A total of 42 viaducts arranged in 2 directions reach a combined length of 10,065 m, while 4 tunnels extend over 1,600 m. In addition, 15 underpasses and overpasses are constructed to maintain smooth traffic flow, supported by numerous culverts at key junctions. The construction process involves massive earthworks totaling 30 million cubic meters, including 24 million cubic meters of excavation and 6 million cub-m of embankment filling. Advanced construction techniques are applied to the viaducts, with 718 m built using the balanced cantilever method and high-tech equipment, while the remaining 947 m utilize the conventional pre-stressed beam method. These structures are expected to rank among Africa's most remarkable engineering achievements in terms of scale, height, and span, highlighting the project's technical significance. The Vogtle Super 3000 asphalt paver is showcased in action on the A10 Berlin Ring, one of the most important highway corridors surrounding Berlin. This high-performance machine is designed for large-scale paving operations. And in this project, it demonstrates its capability to deliver exceptional efficiency, precision, and surface quality under demanding conditions. At the construction site, the Super is tasked with laying both the asphalt binder course and the asphalt surface course across a remarkably wide paving width of 15.50 m. This impressive width allows the machine to cover a significant portion of the roadway in a single pass, drastically reducing the number of required paving runs. As a result, construction time is minimized while maintaining a seamless and uniform pavement structure. The project itself involves a 4.7 km stretch of highway, which was completed in just 4 paving days. This rapid execution highlights not only the machine's high output capacity, but also the efficiency of the entire paving system. The Super is equipped with advanced material handling and distribution systems that ensure consistent asphalt flow, preventing interruptions, and maintaining a steady working rhythm throughout the operation. A key component contributing to this efficiency is the integration with the MT3-2I offset material feeder, also developed by Vogtle. This feeder plays a critical role in ensuring continuous material supply to the paper by transferring asphalt music mix from delivery trucks directly to the paper without contact. It eliminates potential delays and avoids segregation of the material. This continuous supply system allows the PA to operate without stopping, which is essential for achieving a smooth and even road surface. The coordination between the Super 30-2 paper and the MT3000 feeder is highly advanced. Thanks to sophisticated sensor technology, both machines operate in near-perfect synchronization. The automated communication between them ensures that the flow of material is precisely matched to the pause requirements. This level of automation reduces the need for manual intervention, minimizes human error, and enhances overall productivity on site. In addition to its automated material management, the Super 3000 is equipped with a USB sensor system for steering control. This system enables the machine to follow predefined alignment paths with high accuracy. By continuously monitoring reference points, the PA can automatically adjust its direction to maintain the correct position on the roadway. This results in improved paving precision, especially over long distances, and ensures that the final surface meets strict engineering standards. The machine screed system is another crucial feature contributing to the quality of the finished road. It ensures uniform compaction and smoothness of the asphalt layer as it is laid, combined with the consistent material supply and precise steering. The screed helps produce a flawless surface that meets both structural and aesthetic requirements. This is particularly important on major highways like the A10 where durability and driving comfort are essential. Furthermore, the ergonomic design of the Super 30-2 enhances operator control and visibility. The operator platform is designed to provide a clear view of all critical areas, allowing for better monitoring of the paving process. User-friendly controls and digital displays make it easier to manage machine functions, further contributing to efficient and accurate operation. Another important aspect of this project is the reduction of downtime. Because the feeder and paver work together seamlessly, there are fewer interruptions caused by truck exchanges or material shortages. This continuous workflow not only speeds up the project, but also improves the overall quality of the pavement by avoiding joints or inconsistencies that can occur when paving is stopped and restarted. In conclusion, the operation of the Super on the A10 Berlin Ring demonstrates the advantages of modern paving technology. With its wide paving capability, advanced automation, precise steering system, and seamless integration with the MT3 US2i feeder, the machine achieves outstanding performance. Completing a 4.7 km highway section in just 4 days is a clear testament to its efficiency and reliability. This project highlights how innovative engineering and intelligent machine coordination can significantly enhance productivity and quality in large-scale road construction. Hey, let's go! The video presents a specialized high-slope stabilization machine designed to operate safely and efficiently in extreme terrain conditions. This advanced equipment is equipped with a powerful rock drilling system featuring a drill bit diameter ranging from 45 to 76 mm and an impact power of 19.4 kilowatts, enabling it to penetrate corridor rock surfaces with precision. The machine can reach working heights of up to 20 m, making it ideal for steep slope reinforcement tasks. A basket platform with a load capacity of 250 kilograms extends up to 24.6 m, allowing operators to perform anchoring, drilling, and inspection work at significant heights with stability and safety. In addition, the machine integrates a cement injection pump with a capacity of 35 L per minute and a pressure of 40 bars, ensuring effective grouting for structural reinforcement. For surface stabilization, a concrete spraying pump delivers up to 26 cub/m/hour at 60 bars pressure, reaching heights of 23.7 m, making the system highly versatile and efficient. The video presentation highlights a leading construction company recognized for its strong expertise in large-scale infrastructure projects. Over the years, the company has successfully delivered numerous works in tunnels, transportation systems, and massive superstructures, proving its reliability and engineering excellence. With an impressive portfolio, Osgunninsid has completed approximately 275 kilometers of railway lines, 17 bridges and viaducts, 50,000 m of conventional tunnels. Music and 25,000 m of tunnels constructed using advanced tunnel boring machines. These achievements demonstrate not only technical capability but also a commitment to innovation and precision. Driven by sustainable growth, the company focuses on both local and international flagship projects aiming to contribute to modern transportation networks by combining experience, advanced technologies, and a skilled workforce. Osgunninsid has become a trusted partner in the industry. Importantly, it continues to prioritize environmental protection and human safety while pursuing long-term technological and economic development. The installation of the new railway bridge at Cow Lane began with the delivery of prefabricated bridge units to the site. These large concrete and steel structures were transported using self-propelled modular transporters, SPMTs, which maneuvered the components into position with high precision. The new bridge sections were carefully aligned and lowered onto pre-prepared foundations during a short rail possession period. Once the new bridge was in place, the surrounding area was backfilled and teams quickly proceeded to restore the railway infrastructure. Track beds were reinstalled, followed by ballast spreading and precise track alignment. Rail welding and tamping operations ensured the new tracks met operational standards. Overhead line equipment and signal structures were also installed and tested to integrate with the upgraded rail system. With the railway components complete, attention shifted to road reconstruction beneath the new bridge. Layers of subbase and asphalt were laid to form the carriageway. Retaining walls and side embankments were built or reinforced, and drainage systems were installed to prevent flooding. The team then completed road surfacing, added road markings, and installed safety barriers and lighting. As part of the broader project scope, construction began on a new dedicated pedestrian and cycle route. During this phase, the old bridge remained accessible for pedestrians and cyclists, though cyclists were advised to dismount due to narrow space. Construction activities were carried out continuously in multiple shifts to meet the limited time frame. The time-lapse footage highlights the efficient coordination between BAM Nuttall and Network Rail, demonstrating how large-scale rail infrastructure can be upgraded within days, minimizing disruption to both train services and local traffic in Reading. The construction of the Anani's cutting realignment project unfolds through a carefully coordinated sequence captured over 2 years using 3 time-lapse cameras installed by ENFX. The process begins with extensive site preparation along a 5 km corridor stretching from Melton West to the eastern side of Bakey's Marsh. Crews clear vegetation, remove topsoil, and reshape the rugged terrain to create a stable foundation for the new highway alignment. Earth-moving equipment operates continuously, cutting through hills and redistributing material to form embankments and level roads. As the formation takes shape, drainage systems are installed to manage water flow across the site. Culverts and channels are constructed to prevent erosion and ensure long-term stability. At the same time, bridge structures and retaining walls begin to rise, supporting the highway as it passes through challenging sections of the cutting. Next, layers of pavement are progressively laid. Sub-base and base. Materials are compacted with precision, followed by asphalt surfacing that defines the final roadway. The time lapse clearly shows the transformation from raw earth into a smooth engineered highway. In the final stages, safety barriers, signage, and line markings are added. Landscaping works complete the integration of the road into its surroundings. Step by step, the project delivers a modern highway connection, improving traffic flow and safety along this critical route. Heat. The V07 viaduct of the Coimarma Motorway Port Connection Road is a landmark infrastructure project designed to strengthen logistics links between the highway network and the port area. Built across complex terrain with significant height differences, the viaduct plays a crucial role in ensuring smooth, safe, and uninterrupted traffic flow for heavy vehicles serving the port. The bridge has a total length of 875 m, with a maximum pier height of 137 m, making it one of the most technically demanding structures along the route. To achieve this, engineers adopted a reinforced concrete pre-stressed balanced cantilever method, a solution well suited for long spans and deep valleys where ground access is limited. Construction required approximately 50,000 cubic meters of concrete, reflecting the massive scale and structural strength of the viaduct. One of the most remarkable aspects of the project was the use of 12 form travelers, operating simultaneously, allowing multiple segments of the bridge deck to be cast at the same time. This synchronized approach significantly increased efficiency while maintaining high standards of precision and safety. Each segment was carefully poured, pre-stressed, and balanced step by step, ensuring stability throughout the construction process. Despite its size and complexity, the entire viaduct was completed in just 1 year, demonstrating exceptional planning, coordination, and engineering expertise. Today, the V07 viaduct stands as a symbol of modern bridge construction, supporting regional development by providing a reliable and high-capacity connection between the port and the Coimarma motorway.